It is part 2 of section 12.2. In the first part, we considered the very first machine learning classifier called the perceptron. The perceptron uses thresholding activation. In the second part, we'll study Adaline, the adaptive linear neuron. Adaline is minimizing continuous cost function. Continuous cost functions allow the machine learning optimization to incorporate advanced mathematical techniques such as calculus. The objective function is differentiable, so that we can use calculus techniques. Okay, here in this figure, we try to visualize the difference between perceptron and the Adaline. In perceptron, the net input, and after getting that input, now thresholding is applied, and the thresholded the estimation is compared with the label, and then that is used to update the weight. That's the algorithm, perceptron. And in Adaline, the net input is passing through this identity function, which means that the net input is used without change, and that is compared with the label, and the difference is used to update weights. So eventually, there's no thresholding, so that the objective function is continuous and differentiable. So along with this identity activation, and we try to update the weights. And then after training, once the new points came, then now after getting the net input and the final output will be obtained after thresholding. But in training, we don't use any thresholding in Adaline. Here. And the Adaline learning is formulated in this algorithm. Now, for given data set, now we have to find the weight, W, and bias, and W0 or B. Now, activation function is identity function, but we are trying to use the notation phi here. And the objective function, or the cost function, is the sum of square error. Now, there's half the summation over the points, and yi minus zi. Zi is the net input. So this portion is the same as this one. Okay, that is now, okay, yi and minus, okay, that is here W1 x1 plus W2 x2 and so on, and then final will be WD xd and plus b. Right? So that's exactly this one. Of course, over there, then I for x is given in this way. Okay. That's the same as this one in detail. Okay. Now, for this objective function, we try to use gradient descent method. So the direction is minus the gradient of the objective function. So we'll try to find here minus gradient and scaled by eta. And with the same, for the bias, we are doing the same way. Of course, this one is w directional derivative, so it's gradient. Now, this one is, in fact, a partial derivative in b direction. And eta is a positive number, and of course that is small. That is called the step length or the learning rate. Okay, let's try to get the derivative. Once we try to get the derivative with respect to wj, then somewhere here wj will be here. If we try to make derivative for this term, then 2 will go to the front and cancel with this half, and then this term, okay, that is exactly this one, and then here by using the chain rule, and the coefficients of wj will be xj. There's xj with this negative, so that minus xj. So that is wj directional derivative. And also, if you try to get b derivative, partial derivative, then similarly, the 2 will go front, and this term, and coefficients of b is minus 1, so that we have over here minus 1. So that is partial derivatives. And in vector form, we can get this one. So the correction vector for w is minus gradient scaled by eta. But already the gradient will have negation here. So here cancelled in eta scaled by the vector form of negative gradient. Okay, what's the same, eh? Now, but this one is simply the this term with negation of this term scaled by eta. Okay. You can implement this Adaline quite easily by using the perceptron, the class program. But anyway, you can also implement quite a little bit different way along with metric vector form. Okay, let's see on here implementation technique. Okay, for each point, okay, x is given in table. So therefore, each xi, each data point, ith one, we are here in front of the point, we put 1, and then that's called ai. And also, we try to consider the combined the variables b and w, combined weights, in fact. Then zi, okay, b plus w transpose xi, that can be written as ai w tilde. Quite easily you can see that. Now here, that is, now if you consider this dot product, this is considered as a row vector, that is considered as column vector, so that you can easily see that this dot product is the same as this one. Okay. Now, A, once we define A, is the vertical stack of that row vectors, then that is the same as now from x, in front of the x, you are putting a vector of 1, all one vector is now stacked in front of x, then that is A. For each point, 1 is in front of here, so that it's same as that. Now, in metric vector form, the objective function considered in the Adaline algorithm, that one, can be written now y minus a w, so that here we can write in this way. So half y minus a w tilde norm squared, that is exactly same as the original Adaline objective function. Now when you try to get the gradient of this objective function, then simply you can get it quite easily in by using some metric algebra. You can find the derivative with respect to this combined weight, and that is here minus A transpose y minus A W tilde. And we can use this one to solve one example. Okay, let's see this example. Now the data set and labels are given in this way, and we try to use this data set to train the Adaline classifier. And it's a simple toy problem. And now here there are 3.11 and 0, minus 2, minus 2 and 0. And 3.1 is for class 1, the other one is for class minus 1. And we'll try to do 2 iterations of gradient descent method for the Adaline model. Yeah, that is now the gradient, so that use this form to get the change correction vector. Okay, that one is now, okay, in the beginning, we start with 0 initialization, and eta is 0.1. Now, for given data, we try to put all one vector in front of x, and that is a. So this portion is the same as this one. Now, all one's vector is attached in front of x, that is a. Now, initial weight is 0. Now, for this gradient is minus A transpose, and then y minus A W0, but W0 is 0. So that we have that, and simply we have 1 minus 3 and 3, and W1 will be obtained from W0, and minus here eta, that is now 0.1, and this is the gradient. So we got over there the gradient. So we have this result, which is W1. Now from W1, and we try to get again for the second iteration the gradient at W1. There's again, we have this formula, minus A transpose, y minus A W1. Then we have this portion is same as this one, and minus A transpose, after multiplication, we have that. Now, W2 is updated from W1 by adding an eta and minus gradient. Okay, so we will share this one. This final result, and after 2 iteration, is representing now that is a W0 or B. Okay, that is this one. And W1, X1, W2, X2 equals 0. Okay, now go back to the data points, 1, 1. Okay, let's try to visualize these points. Okay, in the beginning, we have 30 points. This is 1, 1. That is 1 point. And 0, minus 2. Okay, 0, minus 2, minus 2, 0. So that we have now another point here and another point here. That is minus 2, minus 2. We have 30 points. And this one is class 1. These two are class minus 1. Okay? And then after 2 iteration, this line can be easily visualized. Okay, move this one to the other side, divide by 0.41, that is almost quarter. Okay, so that about quarter passing this one, and now line is like that. This one. Of course, this is about quarter, a little bit moved it this way. But anyway, this line is between the class 1 and points in class -1. So it is working, it's converging. Probably when you do more iteration, then it's approaching around somewhere. Okay. When we design machine learning algorithm, then we have to decide sometimes the parameters earlier than execution. So a hyperparameter is a parameter. Those value is set before the learning process begins. So for example, the learning rate is a hyperparameter, and also the number of maximum iteration or epoch is hyperparameters. Okay, iteration means one update. In each iteration, we try to update the weights. So a number of iteration means number of updates. Now, epoch means that is the number of passing all the data points. In perceptron, we are trying to use 1 point in each iteration. So for example, we have 100 points. Then after 100 iterations, 1 epoch is finished. But for Adaline, we try to use all the points each time so that 1 iteration is the same as 1 epoch. So epoch and iteration, these words are used in machine learning in this way. For the hyperparameter learning rate eta, you have to choose eta small. If it is large, if it is too large, then the iteration is not really converging. And after a certain iteration, it starts blowing up so that you cannot get a convergence result. You have to choose the eta small enough so that it is stabilized. However, if you choose the eta too small, then convergence is slow. So there, the eta, the learning rate, must be chosen very wisely, and it's not easy to do that. So there is some technique so that you can set the learning rate automatically. So it's working. You don't have to worry about too much, and automatically chosen. So the convergence is well achieved. Now, for perceptron and Adaline, we considered the data set having only 2 classes. What if we have more than 2 classes? Rather than cats and dogs, and we may try to classify cats, dogs, and elephants. So we have 3 classes. In that case, we need some extra technique. But the classifiers developed for 2 classes will be used for multi-class classification. Let's see this figure. We have 3 class data set, and plus and 0, minus points, so that this is a data set having 3 classes. Now for that one, the major technique is 1 versus all, or 1 versus rest. And in this strategy, we try to train the algorithm 3 times, and 1 versus the others. So minus versus O and positive. So that is now W, okay, for that one. Here W minus is trained so that this line is made. and this minus points versus everything else. So we have that on. This is now red line, and plus versus O and minus. That one is now the blue one, plus point versus the others, and we get this one. For O versus plus and minus, that is WO here, and this versus everything else. So we have green one. After getting these three classifiers, and we try to get, and for new points, we evaluate the value, that input, and among them, we try to choose the class showing the maximum value. Okay, let's see here. Okay, for example, a new point X is here now. Then apparently, this point should belong to this minus class. Now, that one can be achieved quite easily through that one. Now, for this W, that W minus, this value, okay, this side will be positive, that side will be negative, of course. And now this line is in fact, and in form of this one, B plus, now W transpose X equals 0. So that along this line, this classifier will have a value 0, and this side positive, that side negative. So okay, so from this line, it's a negative value. Now, for this green one, of course, that side is positive, that side is negative. So we have here now, okay, from red one, this negative, from green one, this negative. Similarly, from blue one, we have that negative. Of course, in blue classifier, along this line is 0. Now, these negative values will have, there are 3 negative values, but this point is far away from this green line. Again, far away, farther than from this line, so that this negative is largest from this side. And this is negative, but it's smaller. And again, this will be smaller. And in negation is far away, so that in fact, among these 3 values, that side will be the maximum. So that point should belong to this negative class. Okay? So by using such mathematical tool, we can find some multiple class classification, and one versus all or one versus rest. And in modern the machine learning society, and multi-class problems are being solved in this way. So even though we consider only 2-class classification algorithms, we can use it for multi-class classification, right? Okay. Okay, that's the end of the section. Thank you.